Good morning, everyone. This is week 8 of ECE 2002. We're going to focus on reviewing for the final exam. We're all done with quizzes, so your quiz score that you see on Brightspace should be final. Obviously, we're done with exam 1 and exam 2. So, make sure those scores are correct as well. If you see anything wrong with homeworks 1 through 5, let us know. We're still going to grade homework 6, within the next couple days or so. And then, of course, we'll grade the final exam. So this is the chance to let us know if anything appears wrong with your exam scores or with your homework scores or the quiz scores, though the quizzes are pretty cut and dry. Other than that, please make sure you fill out the survey, the instructional data processing, course survey. The response rate, definitely looks good. Or the response rate is, determined or helps determine my performance. So I appreciate higher response rates. Highest response rate I've ever got was 2/3, so 67%. So yeah, if we could beat 67%, that would make me really happy. Other than that, I can't really think of too much other than we're going to prepare for the exam. I don't have too much prepared for today, or I guess I prepared a fair bit within the last couple hours, but what do we want to see? Is there anything you want me to basically give the same lecture style again? Lectures, yeah. Let me know if you want to see anything lectured in a more formal lecture style. Riyadh asks, are you keeping homework 7 as it is? Well, let's just say that it's more important to put something down for homework 7 than it is to get it right at this point. We will probably grade that one entirely for completion just because we've run out of time to do grading. And it'll probably take too long to do all the final exam grading. So, but you never know. If I feel super motivated, I might grade everyone's exam. I might grade everyone's homework 7s anyway. Number 6 left, yeah. So yeah, definitely make sure you do that. Also, please make sure you put your name on your homework. Like your name will probably be worth like 26 points or something like that. So please make sure you put your name on your homework. As for the structure of the final exam itself, 8 questions total. The first four questions will be from old material, though there might be a little bit of a lecture set 6 twist on the 2 MOSFET problems. So you can probably expect 2 different MOSFET problems. You'll probably see something related to Laplace transforms. Yeah, I mean, you'll see something else from exam 1 or exam 2 basically make a reappearance. So, keep that in mind. And then the next 4 problems will be basically new material. So lecture set 6, so like maybe Miller effect or something like that. Butterworth filter design, and then real inductor capacitor resistor models and real transmission lines. Yeah, there will be 8 problems. I mean, basically, I don't want to say all of them will be a circuit problem, but like probably 6 out of the 8 of them, roughly speaking, will be circuit problems. They're going to be about the exam length. We were originally going to do 10 problems, make it twice as long as a midterm exam. It'll still be twice as long, but the amount of time you receive will still be 2 hours. But we cut it back to 8 problems. The transmission line problems you get will be very similar to homework, just because we haven't had time to really do much with them. Okay. I will say the transmission line problems will either be really similar to homework, or it'll be like one of the end-to-end models, like the the nominal pi model or equivalent pi model. All questions have Bode plots. Not really, but there will be Bode plots almost certainly in some form. Final exam is 2 hours. Adrian's not here, otherwise, I'd say all problems are graphical convolution problems. But no, for the first 4 problems, you hopefully can kind of know what are the big things we've been covering, what to expect there. Okay, AJ, it's probably not going to be solving an ODE. I guess you never saw the whole statistics for exam 1. Those are kind of private with the teaching staff. But like, since pretty much everyone got that problem right on the first exam, or at the very least, did reasonably well enough, got 12 points out of 20 or something like that. That problem's probably not making a comeback, just because it already tested something. People satisfied that learning objective. Lovely question. Graphical convolution. You liked it where the graphical convolution was 0? Okay, let me share my screen. So people have been asking, where can I see the graded exams? So if you go to Brightspace and then you go to exams, exam 1, the bottom one is, ECE 20002 summer 2022 exam 1 solution. So you can basically see how I worked out exam 1. It's got the statistics and everything like that, in case you were wondering. So this is how I worked out exam 1, including all my messiness, how the points were assigned and everything. So yeah, everyone did, for the most part, everyone did well on this problem. So it's probably not making a comeback. You're probably going to see some form of amplifier on the final exam. You're seeing probably 2 forms of these. Could have a switch circuit. That's fair game. So people in general did well with the ODE portion of the class, so I don't feel the need to rehash it too strongly. It might be a combination ODE and convolution. Some people need another chance at convolution. So if you go to exam 2, you can see the summer exam 2 solution. Again, here are all the statistics, my verdict on how things went. You can see for problem 1, we like to start with a nice, give me question. So or at least it's supposed to be a give me question. So for this general system where apparently it didn't really show up at all, y of t is x of t convolved with h of t, with my little 6-pointed star there. Integral from negative infinity to infinity, x of tau, h of t minus tau d tau. Y of s in the frequency domain, y of s is equal to x of s, h of s with capital letters. And graphical convolution, make sure a lot of people did not do the graphical convolution correctly. Because I kept this h of t in place, moved the triangular function around. So, reflect this so it goes from -2 to 0, and then shift it forward 3 so it'll go from 1 to 3. And then notice this is equal and opposite components, so positive here, negative here. Answer was 0. Took me a while to draw this circuit correctly, but here's what I was looking for in the circuit. Problem 2 is way too hard. You and I had a little bit of back and forth, and we tried to. We said, we think this problem is possible. It just hardly anyone got this problem right. So, you're not going to see anything like problem 2 on the exam where it's just like this sort of guided walkthrough of how to do an inverse Laplace transform. Probably not going to see anything like that. It's just a little too tough. Or if you do see something like this, it'll be a little bit simpler than this transfer function right here, which is a very complicated transfer function. Most people did pretty well with problem 3 on the exam too. Identifying the poles and the zeros. Make sure you include the multiplicity when you identify the zeros. So you can see there's a little 2 hanging out there. So it's the zeros of multiplicity 2. You have to get both part B and part C right in order to be able to equate the transfer functions. So, part C with the circuit was just voltage division. So it's the impedance of the capacitor, SL, over the total impedance of the circuit, R plus 1 over SC plus SL. I don't like complex fractions, so get rid of the SC in the denominator and work it all out. And yeah, you basically equate things. So you say 12 is equal to R over L, and 100 is equal to 1 over LC. I thought more people would get problem 4 right than they did. I really didn't. I mean, like, maybe they spent more time on problem 5 instead because we covered Bodie plot so heavily. But like, I thought we were pretty clear on how to do a resonant frequency. But yeah, you find Zn of S, and then you get just the imaginary part after you simplify a bit. So that requires multiplying top and bottom by the complex conjugate of the denominator. Set the imaginary part when you plug in j omega to 0, and you should get 1 over square root LC minus RC quantity squared. And then you can figure out that what the R has to be for the given values. And then for these values, you can figure out the quality factor of the circuit just by looking at this transfer function right here. Should get that 1 over RC is equal to, or excuse me, R over L is equal to the bandwidth. And then remember, quality factor, it's the center frequency, which is equal to the resonant frequency. So you have to use the resonant frequency you got in part A in order to get the quality factor correct. I gave you 4 points out of 6 points if you got it correct, using the approximation that the center frequency is the natural frequency instead of the resonant frequency. And then most people did pretty well, except me, strangely enough, with the Bodie plot. I screwed up log of 1600 divided by 400. But you just bring this down so that it's at 12 decibels, then there's one bend and it goes down. And then this basically changes at 2, and then at 20, it reaches negative 90 degrees, and then it flattens out again around 200. When Jaya wants to go over Bodie plots, I gave myself 102 out of 100. I thought that was fair. Of course, you have to, if you look carefully, I gave myself more time than the allotted time, so that's where it's unfair. Complex poles. Problem 2. AJ, bro. Bodie plots. That you still am. You would, if you want to know if it's just by looking at the transfer function, you would have to basically extract the bandwidth, extract to the resonant frequency. Hopefully, it's one of the nice parallel or series ones. Get the quality factor. If the quality factor is greater than a half, it's underdamped. Equal to half, critically damped. Less than a half, underdamped. Overdamped, rather. It's really hard to know just by looking at the transfer function. People want to go over Bodie plots again. Okay, I guess I can do that. Open homework review exam 2. Alfred is cool. It's great if you're a Mac user. Otherwise you'd see me going through my file system and like I don't want the China judgment I get for everything, for everyone being able to see that. When I was an undergraduate, I took time to organize my files. When I became a graduate student, it became a never type of thing. So here is, our transfer function. I'll just review this one again because it's got complex poles. Seems to be what people want to do. So h of s is -2 s minus 2 over s squared minus plus 10s plus 169. So this is a 5, 12, 13 right triangle. So we complete the square of the denominator to get s plus 5 quantity squared plus 144, which is just 12 squared. And then we still have s minus 2 in the numerator. There's a 0 at +2 and a pair of poles at -5 plus j12 minus 5 minus j12. If you get it into this form after you complete the square, the real part of your complex pole is at negative this value, and then you have plus or minus this value as your plus or minus j this value once you square root it as your imaginary part. So -5 plus j12 minus 5 minus j12. Or you could just, if you think that's confusing, just run the quadratic formula on s squared plus 10s plus 169, and you'll get s equals -5 plus or minus j12. Completing the square is faster though. So, because when you complete the square, it tells you basically the real part, negative of that, the imaginary parts, plus or minus the square root of this, and also the distance from the origin, which is square root of that. What questions do we have about this so far? We're good at getting the poles of, extracting the actual critical frequencies of complex poles, getting the real imaginary parts too. So that's the pole zero diagram. We'll skip the impulse response and plot it, go straight to the Bode plot. Okay, so we're going to use this transfer function, and we're going to do, establish the critical frequencies. So we know we're going to have a critical frequency at 2 radians per second, and we'll have basically, that's a 0, and we'll basically have effectively a double pole at 13. Why 13? Because that's the distance from the origin. So when we do h at j omega, remember, we're concerned with basically complex frequency as distance from the origin interpretation, not the pure distance along the imaginary axis. So we basically get an effective double pole at 13 radians per second. So basically, we have, first thing we're going to encounter is a 0 at 2 radians per second, then the double pole at 13 radians per second. So, we should basically run from 10 to the -1st up to 10 to the 3rd on our logarithmic frequency axis to get the interesting parts involved. Because it needs to be at least one order of magnitude before 2. So, we'll just make that -1. And it needs to be more than an order of magnitude plus over 13. 100 won't do, so we'll do 1,000. So then we figure out what happens is we plug in s equals 0. So when we plug in 0, we'll get -2 times -2 over 169. So we'll get +4 over 169. Where does that end up being? Well, that ends up being, whatever 20 log of 4 over 169 is, which is -32.52 decibels. So because we don't have any sort of 0 at 0, we know we're going to basically start our magnitude response with a flat slope at that value of -32.5 decibels. Our phase response is going to start at 0 because, there's nothing that would make it start at anything other than 0. before that 0 at 2 radians per second. We're going to apply all the pole and zero rules in turn, and then we're going to figure out what happens if we plug in s goes towards infinity. As s goes towards infinity, we're going to be left with basically something that goes to infinity and something that goes to over infinity squared. So you figure out what's going to happen. Well, that's basically going to say we're going to go to infinity with a slope of minus 20 dB per decade. Because basically it's like, this basically behaves like 1 over s as s gets really large, or, negative 2 over s if you want to be really precise. Whoops. And then our phase response, well, let's see, we're going to have start at 0, encounter a 0, and then encounter 2 poles. So that means we're going to end at negative 90 degrees, because we're going to have plus 90 degrees minus 180 degrees. So that ends at negative 90 degrees. That's something I got wrong when I was making the correct answers for the quiz on Friday and Saturday. Whoops. Everyone should have the correct amount of points from quiz 5 now. And then we have to do an angle wrap, negative 180 to 180. Why does it say that my phase is? Okay, I said something wrong about the phase response. Oh, because the 0 is in the right-hand plane, instead of getting a contribution of plus 90, it's a contribution of negative 90 degrees. So we'll get a negative 90 degree contribution because it's a right-hand plane 0. And then because these are left-hand plane poles, we get minus 90, which is equal to negative 270 degrees. Or it's going to basically go from 0 degrees, go to negative 180 degrees, wrap back to positive 180 degrees, end at positive 90 degrees. That's what I said wrong. Got to be careful here. So here's basically the plots we get. So remember, on the exam, I don't need the curvature. I just need the straight line piecewise linear approximation. So it'll be basically start at negative 32.52 decibels. We get a plus 20 dB per decade slope, and then minus 20, minus 20, so negative 20 overall dB per decade slope once we get past 13. There's some resonance going on right here, so that means our actual, magnitude response will be greater than the value predicted by the asymptotes. And then here, we basically start at 0. We get a negative 45 degree per decade slope, and then we'll get minus another 90 degree per decade slope, so minus 135 degree per decade. That takes us to here. Then we're left with just minus 90 degree per decade slope, and then it zeroes out. And remember, that's what happens after you wrap it around. So that would be a pretty hard one to do, probably a little too hard to do on the exam because of the wrap, but you kind of get the idea of what's going on, I hope. What questions do we have? Talk about the zeros in the numerator. Okay, well, the zeros are always in the numerator. So here, we get an s minus 2. Because it's a right-hand plane 0, that means the phase behaves opposite what we expect. However, we still are basically going to get, a plus 20 degree per decade or plus 20 dB per decade slope when we hit it on the magnitude response. But because it's a right-hand plane 0, as shown by our pole 0 plot. Okay, come on, preview. You know what I'm trying to do. Because it's a right-hand plane 0, it's going to be a negative 90 degree per decade, or negative 45 degree per decade slope instead of a instead of a positive 45 degree per decade slope. So that is what causes it to be like this, where it slopes down instead of sloping up first in the phase response. And that just comes from our good old lecture set 5 rules on slides 30 and 31, if I remember right. Well, I guess it was old 30 and 31. This is the new process for drawing the Bode plots. Review this. We did this. We identified the zeros and poles, critical frequencies associated with them, which are the distance from the origin. Figure out the logarithmic frequency axis we need to draw. Figure out what happens as omega goes to 0. Vertically position the magnitude response. We didn't have to do anything special. We just used the value as omega goes to 0. Pole 0 rules in turn. Counted multiplicity. Omega goes to infinity rules. And then you don't have to do this on an exam. So rules for poles, again, negative 20 dB per decade at the critical frequency. This is what happens actually at it. We don't really care. The phase plot decreases 90 degrees over 2 decades centered on the critical frequency, but a right-hand plane pole, an unstable pole, will cause a 90-degree increase in phase angle. For a left-hand plane 0, remember it's half plane, not hand plane. It's plus 20 dB per decade slope for every 0. And then you get an increase in 90 degrees over 2 decades centered at the critical frequency. However, a right-hand plane 0, I swear I fixed that. That should say 0, causes a 90-degree decrease in the phase angle. And, it's not stable or unstable. Riyadh asked for inverse Laplace with complex conjugate roots. So if we go back to the table of contents, then we go to homework, solutions. You can see homework review, final exam. But here's an inverse Laplace transform problem with complex roots. So a little challenging. We definitely can't do repeated roots. So here's the inverse Laplace transform: s squared plus 36 over s cubed plus 15s squared plus 639s plus 625. First thing we do is say, okay, the impulse response h of t is just the inverse Laplace transform of the transfer function. It's Laplace transform pair. Best to work with the factored form of the transfer function. So you break out tools like Vieta's formulas, you break out the rational root theorem, whatever, and then you'll get that, okay, one of your roots is s plus 1, or, the term corresponding to that, root of -1. The other one is going to be s squared plus 14s plus 625. Factor this one out, and you see that's a 7, 24, 25 right triangle. So you get s plus 7 quantity squared plus 24 squared. And then, you'll see that that is just, square root of, or 25 squared right there. All right, so you got a linear term multiplied by this quadratic term with a linear part. So you'll get a1 over s plus 1 plus a2s plus a3 over s plus 7 quantity squared plus 24 squared. So remember, because this is a irreducible quadratic term, and you need to have a linear term plus a constant term in your numerator. Clear the fraction, so we'll get s squared plus 36 on the left side, and then we'll get a1 times the irreducible quadratic plus a2s plus a3 times s plus 1. So we can solve by plugging in different values. So plug in s equals 0. We'll get 36 equals 625 times a1 plus this becomes 0 plus a3 times 1. Plug in -1 and everything on the last part goes away, and you're left with 37 equals A1 times 612 plus 0 plus 0. So that allows you to solve for A1 directly. And then you just need to choose one other value. Now, Riyadh asked for the cover-up method, but I don't like to do the cover-up method when I know I'm going to have to do things the formal method anyway. I know I can't get, because I have this silly affine term right here with the linear and the constant part, there's no choosing two values such that you can use the cover-up method. So I just do everything formally. So I just choose a convenient value, s equals +1. It kind of matches the -1 case. But you'll get 37 equals, 8 squared plus 24 squared is 640. And then you'll get A2 plus A3 times 2. Solve the system of equations. A1 is equal to 37 over 612. A2 is 575 over 612. And A3 is negative 1093 over 612. Feel free to break out your calculators and use fractions or decimals at this point because it's a little easier. So we rewrite this using our known coefficients now from partial fraction expansion. H of s is 37 over 612 times 1 over s plus 1 plus 575 over 612s minus 1093 over 612 all over s plus 7 quantity squared plus 24 squared. We need to get an s plus 7 in front of this term. So we'll break it down so that this is an s plus 7. But if we add 7 here, times its coefficient, we must subtract 7 times 575 over 612 from the remaining part. Big number right here. Minus 3,709 over 612, 1 over s plus 7 quantity squared plus 24 squared. So we manipulated we manipulated, fixing that spelling mistake while I see it, and we massage the side-like term. So we need to get, 24 in the numerator here. So we put 24 in the denominator. So we get minus 3,709 over 14,688. Plug things into your calculator. You'll get the transfer function is h of t is equal to quantities 0.06046 e to the negative t plus e to the negative 7t times 0.9395 cosine of 24t minus 0.2525 sine of 24t. All of that to the u of times u of t. Don't forget the u of t. Does that help you, Riyadh? I think you're silly if you want to do that. Everything in your Laplace transform table deals with real numbered coefficients. So try your best to get everything in terms of real number coefficients. Even if you don't carry around this term right here, and you said you carry it around like this, you should carry it around like that. Otherwise, you're going to make more work for yourself. You turn what's going to be a one-step process of doing the inverse Laplace transform into a multi-step process of figuring out how to put it into real parts. Salem asked for exam 2, problem 2. Yikes. I'll walk you through the relevant parts, but I think it gets too complicated to do on an exam. So let me. This way I don't have to keep white space open. Thank you, Alfred. I had it somewhere. Okay. Yeah, I decided it was easier to use preview rather than Brightspace. I can change my mind. I'm the instructor. So redraw the circuit after the switch closes in the S domain and give values for all components and sources. So normally you'd be like, okay, you might think it'd be easier to use the current source form of the initial condition on this inductor because the inductor has initial condition, the capacitor does not. However, part B kind of hints at the fact that if you write things this way, it'll be a little bit, the way we're intending. So we reroute the circuit after the switch closes. So after the switch closes, it's not just a battery. After the switch closes, the switch makes it so that it only turns on after the switch closes. So this is actually 50 divided by S in volts. So that's an important thing to keep in mind. So one thing is you transformed your source correctly. This is a battery, but because of the switch action, it doesn't appear, the voltage here doesn't appear until after the switch closes. So 50 divided by S, because it acts like a step function. The resistance of 50 ohms just becomes 50 in ohms. The inductor will just become, inductance is half a Henry. So it just becomes 0.5 S, L times S, 0.5 times S in ohms. And then this is 100 microfarads, which is, 1 times 10 to the negative fourth. But since it's 1 over S times C, it's going to be 10,000 divided by S in ohms as its impedance. If you did admittances, you would have gotten points too, but I don't think anyone really did, to my knowledge or recollection. We also need a source to represent the initial condition on this inductor, because that's part of making the S domain circuit. So you have to recall that, if we have the voltage source, the polarity is opposite what you would expect. It doesn't help contribute to VL of S. It works against it. So you need a minus sign on top, a plus sign on bottom, and then that's going to be just L times IL of 0. So 0.5 Henry times 2 amps is 1 volt. No S involved here. So there is your initial condition. So that was the hard part. Very few people got, all 5 points for, having the source transform, impedances or admittance, the switch being closed. Most people were able to get the switch closed point. The inductor has a source for its initial condition, and then the polarity of the source was correct. Right, VC of S is a function of IL of S. Well, you can see that the voltage in this branch with the capacitor is equal to the voltage in the inductor branch. So VC of S is equal to ZL of S times IL of S minus 1 volt. By KVL, you can say go up, go down. So this works against it. So you get a minus 1 right there. So you get this for VC as a function of IL of S. And then by KCL, you'll get 50 over S minus VC of S over the 50 ohms right here, minus IL of S, because we're trying to write KCL to write an expression for IL of S. So we just leave this as IL of S. And then minus 10,000 over S, in the denominator, VC of S equals 0. So current in through the resistor, current down through the inductor, minus the current down through the capacitor equals 0. We have an expression for VC of S. We substitute it in. And oh my gosh, you do a bunch of algebra. You have to factor out the IL of S term. And you get this monstrosity. IL of S is 2S squared plus 400S plus 20,000 over S times quantity, S squared plus 200S plus 20,000. You got a point if you had an answer without any 1 over S appearing on top or bottom. Very few people got this far. And then I did partial fractions, though there is a really smart way. If you look at the actual hint I gave you, if you're clever with this, you don't have to do partial fractions. You can factor a 2 out and you get s squared plus 200s plus 10,000. And you're like, okay, you do some polynomial division really fast, and you can get something where you don't have to do partial fractions, and you get the same answer right here. 1 plus e to the negative 100t cosine of 100t plus 100e, or e to the negative 100t sine of 100t times u of t. Must include u of t to get full points. That was rough. Problem was just a little too hard. I think noticing the trick here so that you didn't need to do partial fractions was just a little too subtle. The battery doesn't deplete, it turns on. If you treat it, if you were to just write down 50 here, it would basically be an impulse. However, if you say 50 divided by s, it acts like a step. If we wanted it to deplete, we'd say 50 over s plus something, s plus a, and then it would behave like an exponential decay. It would start at a value and decay. So the combination of battery and switch behaves like this voltage source. What else do people want to see to review for the final exam? I also have method of short circuit time constants, method of open circuit time constants, and Miller effect prepared. We have 1 vote for Miller. We just have method of time constant, like not even specifying which one. Miller effect, or Miller theorem. Cool. So this is problem 10.27 in Cedar Smith, 7th edition. I don't even remember what the questions are, but here's basically what the setup is. So here's the circuit. We have V sig and R sig, and then we have this capacitor bridging the negative feedback loop of the sort of inverting configuration of this amplifier. So this is basically an integrator, if you remember our op-amp configurations. So the op-amp, or the voltage amplifier right here, is ideal. Rn is infinity, R out is 0 for the op-amp, labeled A. R sig is 1 kilo ohm, and that the gain at DC is 40 decibels, and we have FH equals 100 kilohertz. So the first thing we're going to do for part A is figure out an equation for the input capacitance. So what is the input capacitance of this configuration? Now you might think, well, there isn't really a real input capacitance here, but because of Miller theorem, we can change this bridging capacitor into an input capacitor and an output capacitor. So we can say, V sig, R sig, and Cn, and then we'll get C2 and then the output. Because VO is equal to A times VI, Miller's theorem can be used. So the input capacitance is ZCN, just looking right here what the impedance should be. 1 over SZC, or 1 over SCN equals 1 over SC, the original capacitance, times 1 over 1 minus A, because this is the formula for what this capacitance should be, or what this impedance should be after the Miller effect. So notice, you can equate the parts in the denominator. You get that Cn is equal to C times 1 minus A, where A is a negative number. However, you could treat it as a positive number and say C1 plus absolute value of A. I like to just let A be the negative number. How do we know it's a negative number? Because this is an inverting op-amp configuration. So the overall transfer function may be found using the voltage divider equation and amplifier terminal relationships. So overall gain is going to be VI is to V sig as VO is to VI multiplied together. So we know what VO is to VI, that's just A. And then what is VI to V sig? Well, that's just going to be an application of a voltage divider. So it's going to be ZCin over ZR sig plus ZCin. So rearrange this. GV of S is A times 1 over SCN over R sig plus 1 over SCN. You get GV of S is 1, or A over 1 plus SCN R sig. This is the form of a first order low pass filter transfer function. So you can immediately identify that omega H right here is basically 1 over CN R sig. So that's the transfer function that we're trying to get. So let's figure out what the value of A is now for this amplifier. We're told that GV at DC is 40 decibels. So this comes from undoing the amplifier relationship. So remember, in decibels, you just take, to get a gain in decibels, you take 20 times the log base 10 of the gain. So if we undo that, we get that the gain as a number is 10 to the GV at S equals 0 over 20. So A is equal to negative 10 to 40 decibels over 20 decibels. So that's equal to negative 100. And we know we had to take the negative option out of the plus or minus because this is an inverting amplifier configuration. This allows us to also find the value for C. So FH, we said based off of here. So, we were given a linear frequency. We know how to convert from linear frequencies or to linear frequencies from angular frequencies. So FH is 1 over 2 pi times the angular frequency, which is Cn times R sig. So we said Cn was just C times 1 minus A. We now know A is equal to negative 100. So we get C is equal to 2 pi times 10 to the 5th hertz times 101 times 1000 ohms. Work that out and you get 16 picofarads. Because, 1.57 times 10 to the negative 11th farads is equal to 15.7 times 10 to the negative 12, or 10 to the negative 12 is pico. So again, C is a pretty small capacitance right here, but it has a noticeable effect on the circuit. And then you can plot the gain magnitude response. So we said this is a low pass filter transfer function, so you get, behaves like this. And then you have that bend right there where it slopes down to negative 20 dB per decade. And then from that, we can also figure out the transition frequency. So the transition frequency is where the gain equals 1. So you work that out, and that's 10 megahertz. Or, use the other formula you have, which is that the transition frequency is 100 times the upper dB frequency, where 100 was just our circuit gain. Does everyone kind of understand what's going on with this Miller effect question? So by using an ideal op amp, we can, ask a question about the Miller effect separate from your knowledge of MOSFETs. Oh, we got A equals negative 100. Well, the first thing to notice is just because of this configuration of amplifier, we know A has to be a negative number. So, we say, 20 times log base 10 at the absolute value of A equals GV in decibels. So we, first we divide by 20 decibels on both sides. We take 10 to the log, or we take 10 to both sides to eliminate the logarithm. And then since we have an absolute value sign, we take plus or minus sign. So that's how we get A is equal to plus or minus 10 to the gain at DC in decibels divided by 20. Then, of course, we know we have to take the minus sign. Oh, gotta see. Yeah, if you look in the original givens of the circuit, it said, we would get the voltage amplifier is ideal. R sig is 1 kilo ohm. GV of S at S equals 0 is 40 decibels. And the upper transistor frequency is 100 kilohertz. That was a given. Man, someone wants the transmission line question tomorrow? Okay. So we can do method of short circuit time constants, open circuit time constants. I'll try to have Butterworth filter design question ready for tomorrow. And someone wants to see TX line questions. Anything else you want to see, post on Piazza or elsewhere. Difficult one though. Okay, I'll try to make it difficult. Let's do the method of open circuit time constants. That one does not too bad. So here, what we're going to do most likely is rather than have you, draw the small signal equivalent circuit, we'll give you the small signal equivalent circuit. And this time, I'm forcing you to use the equivalent T model. It's a common gate amplifier right here, and I've redrawn the, capacitances in a way that's not obviously that this is from the equivalent T model. Estimate the upper half power frequency using the method of open circuit time constants. Assume that R sub O goes to infinity. In other words, ignore the early effect. According to the method of open circuit time constants, we can turn off all independent sources. Then we consider each capacitor one at a time while open circuiting all other capacitors. That's why it's called open circuit time constants. We do each capacitor one at a time, open circuit the others. Then we find the equivalent resistance perceived by each capacitor. So starting with CGS right here, we see CGS, and we see R sig, and then go into ground because we turned off this source. And then we see 1 over GM connecting to ground with nothing up here because VGS is equal to 0. So, we just see R sig in parallel with 1 over GM. Now for the other capacitor, we'll call this one CL prime, which is CL plus CGD. All it's going to see is RL prime, which, could be RL in parallel with any RD in parallel with any other resistance we have in the circuit up there. So our capacitor CL prime just perceives our CL prime equal to RL prime. Method of open circuit time constants is the upper 3 dB frequency is the reciprocal of the sum of time constants. Be careful here. It's different than short circuit time constants because there it's the sum of reciprocal time constants. This is the reciprocal of the sum of time constants. So 1 over a sum. So we use tau h to denote the sum of time constants. Omega h is 1 over tau h, which is 1 over CGS, RGS plus CL prime, RL prime. You can plug in numbers as you see fit. But that's the answer. Right, because we turned off all the sources, we're not going to get any sort of VGS here. There's going to be no voltage different across 1 over GM. So that means the current flowing through here is 0. Open circuit. Or you could say, yeah, this is just makes current I flow, where the current I is the same current that flows through 1 over GM resistor, and there's no current flowing, so therefore it must be 0. Either way you think of it, AJ. Do we have any other questions we want to do in 3 minutes? Anything else you want to see tomorrow? So we'll go over short circuit time constants, Bioware filter design, and a TX line question. Any other things you want to see from lecture set 8 or the other ones? Tomorrow will be the last day we lecture. Last time you get to hear from me. Exactly. Well, please fill out this course survey if you haven't already. Study hard. Let me know if you have any questions. I'll see some of you in office hours. Let's call it a day right here. Bye, everyone. Deadline. Homework's due tonight.
The survey. When is the survey deadline?
Which deadline?
For the survey?
I think the survey, let me look it up real fast. Instructional data processing. Deadline is August 5th, so this Friday. You're welcome. Goodbye, everyone.